Hey everyone, and welcome back to the channel. Hydrogen is being hailed as the fuel of the future, the key to unlocking a decarbonized world. Governments and companies are pouring billions into massive green hydrogen projects, but many of these ambitious plans, especially in places like Saudi Arabia, Namibia, or Australia, face a very simple yet profound question. Where will they get the water? Fresh water is scarce in these regions, so the only real option is the ocean. But you can't just pump seawater directly into an electrolyzer. It is packed with salts and contaminants that would completely destroy the delicate machinery in a matter of days. The solution is desalination, turning salty seawater into pure, clean water. But here's the catch. Desalination isn't free. It costs energy, it costs money, and it creates its own environmental challenges. Today, we're diving deep into the real cost of desalination for hydrogen production. We'll explore why it's a critical factor for project economics and what developers, investors, and communities absolutely need to know. At its heart, this is a chemistry problem. Seawater has about 35,000 parts per million of dissolved salts. Electrolyzers, on the other hand, need water that is millions of times purer. This means everything. The salts, microbes, organic matter, it all has to go. The technology for this is called seawater reverse osmosis, or SWRO. Think of it like this. You push seawater through a special membrane at incredibly high pressure. Fresh water squeezes through, leaving the salt and other gunk behind. But it's not perfectly efficient. For every 2 gallons of seawater you put in, you only get about 1 gallon of fresh water out. The rest becomes a super concentrated salty brine. But here's the first twist. Even after reverse osmosis, the water still isn't pure enough for an electrolyzer. It needs extra polishing steps to reach an almost unbelievable level of purity. So, desalination isn't a single step. It's the start of a whole treatment process, and every single stage adds to the final cost. Let's talk numbers. A modern desalination plant uses about 3 to 4 kilowatt hours of electricity to make 1 cubic meter of fresh water. Since it takes about 9 liters of ultrapure water to make 1 kilogram of hydrogen, the electricity for desalination is a tiny fraction, less than 0.1% of the electricity needed for the electrolysis itself. Because of this, some people have dismissed desalination costs as insignificant. But that's a huge mistake, and it misses the bigger picture. While the energy use might be small, the cost to build and operate the desalination plant is definitely not. A modern SWRO plant can cost between $1,000 and $2,000 for every cubic meter of water it can produce per day. A huge green hydrogen facility, like the NEOM project in Saudi Arabia, needs thousands of cubic meters of pure water every single day. When you factor in the water loss during the process, the intake from the sea is even higher. This translates to a capital cost of $10 to $20 million for the desalination plant alone, and that's before you even add the expensive polishing systems, storage tanks, and backup equipment. Suddenly, the water system can account for tens of millions of dollars of the total project cost. And then you have the operating expenses. It's not just electricity. You need chemicals for pretreatment, solutions to prevent scaling and to clean the membranes. And you have to replace those membranes periodically. And what about that salty brine we mentioned? Disposing of it is another major cost. Most coastal projects just dilute the brine and release it back into the sea. But this can create environmental problems. The dense, salty water can sink to the seafloor and create dead zones, harming marine life. Regulators are watching this closely, and some projects might face expensive rules to protect the local ecosystem. NEOM, for example, is aiming for zero brine discharge, planning to use circular systems that recover minerals from the brine. If they pull it off, it could set a new standard, but it also adds significant engineering complexity and cost to an already complex project. The economics also change dramatically with size. Small plants are much more expensive per gallon of water produced. Large mega plants benefit from economies of scale, bringing the cost down. For a hydrogen project, This difference could be a few cents per kilogram of hydrogen. It might sound small, but when you're racing to hit a target of $2 per kilogram, every single cent counts. Another tricky factor is integration. Green hydrogen is often powered by solar and wind, which are intermittent. But desalination plants work best when they run steadily, 24/7. Constantly ramping them up and down causes extra wear and tear and increases maintenance costs. This creates a mismatch. Do you build giant water tanks? Do you design more flexible, modular desalination systems? Every choice has trade-offs in cost and reliability. Beyond the technical and economic challenges, there's the issue of public perception and sustainability. Some critics worry that hydrogen production will steal water from local communities. In reality, a big hydrogen plant uses a tiny amount of seawater compared to a large city's desalination plant. The scale is manageable, but the optics matter. In regions where water is precious, any large-scale industrial water use can be a sensitive topic. If the brine discharge isn't managed well, public opinion can quickly turn against a project. Of course, not every hydrogen project will need seawater. Inland projects might use municipal water or recycled wastewater. But for the coastal megaprojects that are grabbing all the headlines, desalination is non-negotiable. That is why major water technology companies are now positioning themselves as essential partners in the hydrogen economy. Looking ahead, innovation could change the game. New types of membranes made from materials like graphene promise to be more efficient. Advanced systems could eliminate brine discharge altogether while recovering valuable minerals like lithium or magnesium. AI-driven monitoring could reduce maintenance and chemical use. These aren't science fiction, they're being tested right now. So, what does this all mean? For developers and investors, it means desalination is a critical system that can make or break a project. The costs have to be modeled carefully from day one. The integration challenges with renewable energy have to be solved, and sustainability can't be an afterthought. For policymakers, it means ensuring that regulations protect the environment without stifling innovation. For investors, a hydrogen project with a vague water plan is a major red flag. The bottom line is this: the ocean has more than enough water, but turning that water into fuel is not free, and it's not simple. The real cost of desalination is hidden in the capital investment, the maintenance, the integration challenges, and the environmental responsibility. If we ignore these costs, we risk undermining the very projects that are supposed to build our clean energy future. The only way forward is to tackle them head-on. If you want to dive even deeper, check out the Green Hydrogen Project Development and Financing course at H2 Hub. Renee Energy. We have a tool called the H2 Hub Schematic Generator that lets you model these water treatment choices and see their impact on project costs. Because while renewable electricity powers the hydrogen economy, it's water that makes it all possible. Thanks for watching. If you found this video helpful, please give it a thumbs up, subscribe to the channel, and hit that notification bell so you don't miss our next one. See you soon.